Imagine a world where you just built a project, and this project turned out so well that you thought, hey, this thing needs a cabinet. Imagine further that all you had to do was measure the board, start a program, and drop just 4 dimensions into that same program. In a minute or two, you had an STL file ready to send off to your 3D printer. Find that hard to believe? Well, think again. The year is 2020 and the process is called parametric programming. Once you learn the process, you'll never have to suffer the drudge work of creating another cabinet drawing again, and it's surprisingly easy to do. Today I'm going to show you my program and how you can custom create your very own. So, sit back and get ready to hand more drudge work off to your computer. After all, isn't that where drudge work belongs? As part of the maker community, sooner or later you're going to need a container to house projects like these. On the left is a kit which included no cabinet. On the right is a scratch-built function generator. It was a quick and dirty project which I never considered permanent. Though rough and crude, turned out to be so useful that I decided to give it a permanent housing. If I decided to buy an enclosure, I would have to search the net for a suitable compromise. As you can see, these things are usually oversized or overpriced. Additionally, they're really not exactly what you're looking for in the first place. Here we have the enclosure we're going to create, though we haven't yet told FreeCAD the size we want. Also notice there are 4 bosses, 1 in each corner, with a hole to accommodate a screw. Looking at the box from the bottom, notice the 4 screw holes, which are countersunk to accommodate a flathead screw. FreeCAD is a real nice tool to do this sort of thing in just one step. We'll cover this tool in detail much later. Again, looking at the top view, I want you to notice the distance of the flat part of the wall. For the current screw size selected, this dimension, including the wall thickness, is always 24.7 millimeters smaller than the outside dimension of the cabinet. As long as you don't change the screw size, this will not change. Later in this series, I'll show you a simple way to make this measurement. Anyway, back to the project at hand. Before we get into this, I want to say that I'm going to deliberately leave cabinet space at both ends of the enclosure to allow space for outboard potentiometers, banana jacks, as well as a barrel connector to supply power. I measured the board with an inexpensive digital caliper, though a simple ruler is more than adequate. The board dimensions are width 114.3 millimeters, height 57.15 millimeters. As you can see from this view, I did the connections with a wire wrap tool. The distance from the pin bottom to the circuit board is 18.843 millimeters. The thickness of the circuit board is 1.55 millimeters. The distance from the top of the board to the highest component is approximately 21.87 millimeters. Adding all of the height dimensions gives a total of 42.263 millimeters. We'll break this total down, giving part to the box top and the rest to the box bottom. These are the 4 dimensions I was talking about at the beginning of the video. We're back again at the enclosure drawing, and as you can see, there is a small spreadsheet insert in the upper left-hand corner of our drawing. Unfortunately, all of the dimensions in that sheet describe the outside of the enclosure. Thus, it will be necessary to calculate these values based on the size of our board. Also notice that I created a sketch which floats above the floor of the box bottom. This is really not part of the parametric drawing. It's simply an aid to check if we made any serious blunders in our box calculations. The width is found by adding 114.3 millimeters plus the 24.7 millimeter box allowance to give us a total width of 139 millimeters. The height is found by adding 57.15 millimeters plus 2 times 2 millimeter clearance. We'd like 2 millimeters of clearance above and below the board, plus 2 times the 2 millimeter wall thickness, giving us a total of 65.15 millimeters. As for the depth of the box top, I've arbitrarily chosen 9.5 millimeters. Adding this to the 2 millimeter wall thickness gives us a total of 11.5 millimeters. Subtracting this from the total board height we found earlier gives us 42.263 millimeters minus the 9.5 millimeters we just chose, plus the 2 millimeter wall thickness gives us a total of 34.763 millimeters. This completes the 4 dimensions we'll need, so let's begin punching these values into the spreadsheet. Before we do, I want to mention that my best computer is suffering an intermittent problem, so I had to fall back to the computer that I usually use for my CNC machinery, which is nearly old enough to vote. If you have a newer computer, it's likely that these response times to the values we enter will be much faster than what you see here. First, we'll enter 139.0 for the width. Next, we'll enter 65.15 millimeters for the height. We'll now enter 11.5 millimeters for the box top depth. Lastly, we'll enter 34.763 for the box bottom depth. We now have the completed box ready to convert to a mesh file and send off to our 3D printer. Before we create these STL files, I'd like to stop and ask you to please hit the red button in the lower right of your screen. It's things like this that give me an idea as to how interested the maker community is in saving time and effort in this matter. If I get a substantial number of subscribes, I'll get the next part of this series out in a week. If not, I'll still do part 2, but it will likely be 2 weeks before I get the second part. So please hit the like as well as the subscribe button. Anyway, back to our model. From the time I began punching these last 4 dimensions into the spreadsheet to the program displaying a model ready to convert to an STL file, took only 1 minute 6 seconds. Seriously? I don't care how good a programmer you are in CAD, or for that matter, what CAD program you're using. No one, and I mean no one, can create a project enclosure from scratch in 1 minute 6 seconds. For our last step, and yes, every CAD modeler has to do this, we need to convert our enclosure to an STL file. First, we need to select the Mesh Design Workbench from the drop-down menu. Then, from our combo view, we need to select the model tree. From our box top tree, we'll go down to the bottom and select Fillet 001. You'll now notice that the box top is highlighted in green. Next, we'll go to the very top toolbar and select Meshes. From the drop-down menu, select Create Mesh from Shape. From the combo view, which has switched from Model to Tasks, select the Standard Option button and press the OK button. You'll now notice the box top has been enveloped in a mesh. To better see the mesh, from the model tree, again select Fillet 001. From the menu directly below, select Visibility True and convert it to False. Although this step is not necessary, it makes it easier to see our box top mesh. Now go to the very bottom of the model tree and notice an entry labeled Fillet 001 Meshed and select this entry. If you look at the bottom row of the top toolbars, you'll notice 4 icons have suddenly changed color. We're going to select the icon which exports a mesh to a file. If you're in doubt as to which one that is, just hover your mouse over each button. An explanation of the button will pop up. You'll now notice a file menu appear, directing you to enter a name for your file. In my case, I'll choose Box Top, then press Save. Notice that I got a message that this file already exists. I'm going to press the Yes button because this file was for another enclosure which has been copied off to my slicer program. We're now going to close our box top tree and open our box bottom tree. Heading to the bottom of that file, we'll select Fillet 003 and notice it gets highlighted in green. To save you from the boredom of watching me repeat this process, I'll just say that from here we'll repeat the same steps we did for the box top. Well, there you have it. A project ready to send to your printer for a fraction of the cost of even the cheapest enclosure you might find on the net. You might now say, but can't a 3D printer also print the holes for your project's shafts and connectors? Yes, but this will come much later in this series. At this point, I have taken you to a place you would be if you went out and bought an enclosure. Except, of course, that this is exactly the size and color that you wanted. Before we move on, take a quick look at this complex printed gear. By the way, that gear is still in service in my shredder. I did that printed gear tutorial a little over a year ago, which generated thousands of views in a very short period of time. Best of all, that tutorial followed the same pattern as this one. You have a complex or tedious problem. By using Parametric CAD with just a few variables, your project is suddenly completed with very little effort. Computers are supposed to serve us, not the other way around. If you're into robotics and/or gearing, check this video out. At the very end of this video, I'll leave a link you can click on to that very series. You've seen my program in action. Now it's time to have a look at yours. The next step on this road is to take a closer look at that spreadsheet. Don't worry, this sheet is far less complicated than the one in your office suite, which I'm sure you've already used.